Hey guys, it's No Pointer here, and today we are building the foundations of a chess engine from scratch. This is because tutorials don't exist, and the ones that do are from 2004 and written in like NCC or something. We're gonna go from hex values that look like your Wi-Fi password to a full chess engine that can outplay you. Um, for making this chess engine, your best friends will be the chess programming wiki and forums. I know, like, you're thinking, why do you need forums? But that's actually where you will get most of your information. And the most important part probably will be the binary to hexadecimal converter. You will see why we need this later on. Now you can see the chess programming wiki doesn't go into a lot of detail about bitboards, but they gave us how to do it using a Microsoft compiler and C++ from 1999. However, I believe this probably won't be useful to you unless you're coding like on a microwave. But I will make more sense of that later using modern C++. Now, for all of you that don't know, this is a chessboard. You should probably learn what a chessboard is though before making the chess engine. But as you can see, the files are vertical and go from 1 to 8, and the ranks are horizontal and go from A to H. This gives us 8 ranks and 8 files, in total 64 squares. Each square can hold one piece. Okay, so let's go back to the microwave compilers. As you can see here, they're defining an unsigned integer, 64-bit integer called U64. But with modern C, we can just do including the C standard integer library and defining an alias for an unsigned 64 integer called U64. So from now on, when we say U64, our compiler will know that's just an unsigned 64-bit integer. This just means it's an unsigned 64-bit integer. It's from the C standard integer library. And unsigned means it can't hold on negative numbers, only positive numbers. If you try to feed it a negative number, it's gonna go madman on you, speaking from experience, by the way. Now to the fun stuff. Don't get scared here in a second, but we can define our board as this hexadecimal value. Now you're asking, what the hell is this? Well, this part over here is just a hexadecimal. It's like a number system, just like binary. So this probably looks useless, but when we convert it to binary, it also looks even more useless, right? We have 8 sets of zeros and 8 zeros in each set. Each one of these zeros represents 1 bit in the 64-bit integer. So when we stack them this way horizontally, they are pretty useless, right? But you will see in the next slide that when we do it vertically, it becomes something much more meaningful. Here you go. So I stacked them vertically and added a space between them to make it more readable. Now it looks much more like a chessboard, doesn't it? See, we have the ranks and the files. Each one of these zeros is a 1 bit and is part of this whole bitboard, hence the name bitboards, because it's made up of bits. Each one of these zeros represents 1 square in a chessboard. So try to think of each one of these bits like real estate. If it's marked with a 1, it means it's occupied. If it's 0, it means it's empty. So here is how we will define the starting position of all pawns in the binary system. So this is kind of counterintuitive, but when we convert this to a horizontal value, you can see the ones at the end of the string, the value. These are called the high bits and represent the white pieces. So white pieces aren't at the start, they're at the end, and black pieces are at the start. We know pawns are on the second rank, so we just put them in the second set of zeros like this. Same for the white pieces right here. And now this binary is pretty useless, but when we convert it into a hexadecimal and add the ULL at the end, which just stands for an unsigned long, this basically tells the computer we're working with 64-bit integers and it's not just a meaningless hex value. Now I'm gonna show you how you can, for example, represent the starting position of white pawns. So as I said, the white pieces go at the end of the value, so white pawns would be at the second rank of the white pieces. And we just define the white pawns as the whole row. Same for black pawns, but we just flip this value, so they go at the start. Now for white knights. We know white knights are right next to the rook, and they are on the first rank. So we just put them right next to the rook, and we put 1 because it's occupied by the knights. And now we convert this to hexadecimal, and we have the starting position of all our white knights as a hexadecimal. We do the same thing for black knights, but just flip it. And now we have both the starting position of white knights and black knights as a bitboard. And I have done all of these values for you in the description, so you don't have to do it because you're lazy, I know. And also we have this. We have all white pieces, so we do it by combining all the white pawns, white knights, white bishops, white rooks, white queens, and white kings. And this will represent all the bits that hold the white pieces, and the same for all the black pieces. And now to just get all the squares that are occupied, we combine the black and white bits. To get all the empty squares, we just flip the occupied bits. This is all pretty simple, guys, and you can find it in the description of the video. Now to get into some of the fun functions. As you can see here, we have a square to bit function. It takes the file as a char and the rank as a char. Now to get the file index, from the file we just remove the letters, so E2, E4, and we're left with the rank. Now to get the rank index, we can just remove the rank from the 1 character. And to get the final bit, we just multiply the rank index by 8, because that's the number of zeros, and add the file index on top of it. Now to use this function, we can start by defining which is the starting position. Let's say B1, that's where the white knight is. And to move it to C3, for example, that's one of the starting moves a knight can do, a white knight can do. So we just go to get the bit from and the bit to. And when we print this, you can see the from, which is B1, becomes 1 bit. And the 2, which is C3, becomes the 18-bit. Let me show you why this makes more sense. This is our bitboard as a 64-bit integer. You can see it starts with 0 and ends with 63. We started with B1 going to C3, so B1 would be the 1 bit, as our function defined that. And we're going to C3. C3 is right here, and you can see it's 18. So our function did get it right. And that's basically it for bitboards, guys. For the next video, I'm gonna be going over bitwise operators. That's what you're gonna need to work with these bitboards. And also like make moves, see if moves are legal, and so on. This series will hopefully tell you everything about building a chess engine. And if you have any questions, you can go to my Discord server and ask me there.